All right, this is our second video over chapter 12, and we're going to look at, in particular, what happens when waves interfere with one another, and a phenomenon called standing waves that plays a really important role, particularly in things like hearing and music. Anytime a wave encounters a boundary, and by boundary, that means a change in medium. Maybe it's a sound wave traveling through air and then it's going to travel into water. Maybe it's the sunlight, even though that's not a mechanical wave, traveling through air and now it's going to travel through glass. Anytime we get a change in medium, there's really three possible outcomes. The wave can be reflected, the wave can be refracted, or the wave can be absorbed. We're going to concentrate right now on what happens when a wave is reflected. And in all honesty, most of the time it's a combination. Part of the wave gets reflected, part of the wave gets transmitted, part of the wave energy gets absorbed, which causes a reduction in amplitude. We're going to look at reflection. If we have reflection with a fixed end, suppose this is a wall, and you have a rope, and you send a pulse through this wall to the rope, and this is fixed right here. It's not free to move. Well, think of what happens when that wave reaches this point, when it's way over here. Just kind of get forward a little bit. This wave is actually pulling up. So the wave pulls up on the wall. If you can envision that wave when it reaches over here, then it'll be pulling up on the wall. That causes the wall to pull down on the wave. That's classic Newton's third law. When it reaches the wall, this pulse right here is going to pull up on the wall will pull down on the wave, and the reflected wave will go back, only it will be reflected. So when you have a fixed end, the reflected wave is inverted. I think it said the reflected wave is reflected. The reflected wave is inverted. And inverted simply means upside down. It's easier to see that if I have just a single pulse. Now, what if that end was not fixed? Let's suppose we change this. And instead of being fixed, we can envision that this has got a ring or a loop, and it's just going around some kind of pole, just something to hold it in place. Well, now, when the wave reaches the end, it is not pulling up on the wall because it's not attached to the wall. So if there's no fixed end, it's going to go up and then it's going to come back down, and the wave will reflect without being inverted. So when the end was fixed, Newton's third law caused the reflected wave to be inverted. But if the end is free to move and it moves freely, then the reflected wave will not be inverted. One very important important concept in the world of waves is something called the principle of superposition. I'm sure you've probably heard of maybe photography where one image is superimposed onto another image. They're occupying the same place. In superposition, two waves are sharing the same position. They're the same, occupying the same space within the medium. Suppose, for example, you have a situation where you have a wave pulse traveling to the right, and in this same row, you have a wave pulse traveling to the left. At some point, they're going to reach the same part of the road. When they do, they will simply add together. The principle of superposition says that the resulting wave, when two waves occupy the same space, the resulting wave is just an algebraic sum. Algebraic sum just means you need to pay attention to whether things are positive and negative. In this case, both are positive. They're going to superimpose. We call this constructive interference. Anytime you have an increase in the amplitude of a wave that's constructive, afterwards, it'll look like this. Now, sometimes people think it looks like the waves bounce off each other, but they in fact passed directly through each other. Now, that's a little bit easier to see if those waves are not identical. In fact, let's change things where we do in fact have two pulses, but one of the pulses looks like this. What will happen now if those are identical sized pulses, when they pass through the same space, you will get destructive interference. In destructive interference, you always have a reduction of amplitude. Now this is perfectly wiped out. Afterwards, of course, you'll see the waves continuing on. That wave is still traveling to the left, and this one's still traveling to the right. Now, that's total destruction. That's not the norm. It might be more common maybe to have something like this, where you have one wave that's a little bit bigger, so when they occupy the same space, you get this small little bubble. But then afterwards, they continue on. So you don't have to have total destruction, but you can see it's an algebraic sum. If this is a height of +1 and this is a height of -2, then this would be a height of -1. Okay. This will come up more in the spring, so we want to kind of just think about this. If you have two waves and they are emanating from identical sources and they are in sync, so we have a wave and you have an identical wave. And I probably can't draw an identical wave, but I'm going to try. If they're exactly alike and they are in phase, that means both waves have their maximums at the same point, both waves have their minimums at the same point. That's going to be a case of perfectly constructive interference if you add those together. You'll get a wave that looks just like it, but with twice the amplitude. If they are 1/2 cycle out of phase, that means when one is at a crest, the other is at a minimum. So, crest, 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 crest. But over here, trough, 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 trough. If they're exactly out of phase, that of course gives you that total destructive interference. Okay. One of the things that comes from this idea of constructive or destructive interference, or interference in general, are standing waves. Pretty much any musical instrument, whether it's a stringed instrument or whether it is a wind instrument like a flute or clarinet, they play those particular frequencies because of standing waves. Now, the book goes into a lot about musical instruments, and we're not going to get that in depth, but I do want to at least look at what standing waves on a string look like. So if you think of something like a guitar string that you pluck, and we want this string to be, say, this long, it will set up a wave when you pluck it like this. When it hits this boundary that is fixed, it will reflect like this. Notice that's not a complete wavelength. To finish that first wave, we would have to do something like this. But it gets reflected and inverted, and we set up a standing wave. It looks like it's simply vibrating around equilibrium like this, back and forth. One of the things that you'll notice about a standing wave is it looks like it stands still. A standing wave will not transfer energy from one location to another because the nodes don't move. These fixed points that we have no motion are called nodes. Both of these endpoints are nodes. The points where you have this maximum vibration, that's called an antinode. Some people kind of want to mix those up because anti certainly sounds negative and they think that's where they're, just remember node is no motion. If we assume that this string right here has a length of L from here to here, this particular standing wavelength, since that is actually one bump in a standing wave, one bump is half of a wavelength, we can see here that the wavelength would equal 2L. It has two nodes. It has one antinode. I'll just abbreviate that. We call this the fundamental frequency. If you pluck a guitar string, that's the frequency you probably observe. Although actually there are multiple waves going on through that string at the same time. And in fact, it's those multiple waves that give each different stringed instrument its own unique recipe for sound. Plucking a guitar sounds different than plucking a piano or a banjo or a violin, any string. They all sound different, or a harp, and you'll see why. This is called the fundamental frequency. One bump, that's the fundamental frequency. It's commonly called F1. We'll call that lambda 1. This is the first harmonic. That's another word for fundamental frequency. First harmonic. What you might observe if we were able to do labs where we had wave generators, and I don't know if any of you have ever seen a wave generator, if we play around with it, we can take that same length, it's still fixed at both ends, and get another standing wave that looks like this. If you've ever played with jump ropes, this was the easy one. That's how you had it when it, but you could shake it up and down and you could make a wave that looked like this. This time, we've got two bumps. We call that the second harmonic. Its wavelength is simply L. It's the length of the string. It takes two bumps to make a complete wave. This time we have one more node, so we have one more antinode. The number of antinodes is always the same as the frequency. One bump, F1. Two bumps, F2. It's called the second harmonic. Or if we're talking about musical instruments, sometimes the second harmonic is called the first overtone. So just if you're reading a problem and it's talking about overtone, they're numbered differently. Some musicians will talk about a fundamental frequency, then the first overtone, the second overtone, the third overtone. If we talk about harmonics, the fundamental frequency is the same as the first harmonic, then the second harmonic. So there's just a slight difference in the number here. Second harmonic is the first overtone. That's what I always remember. The third harmonic will be the second overtone. If we keep going, same length string, only now we're going to get 3 bumps. Notice one of the things that happens usually is the amplitude goes down. In part that's because higher frequencies require more energy, and so energy going into a higher frequency causes less amplitude. Large amplitudes and large frequencies both require energy. I didn't draw that one quite as well, but we'll pretend I did. This is our third harmonic. That's lambda 3. Notice the wavelength is 2/3 of L. In fact, if we go back up here, this one is 2L divided by 2. This is 2L divided by 1. Think about that. We could have written this as 2L divided by 2, so got L. What we've come up with is the wavelength is always 2L divided by N. N is the number of the harmonic. N is also the number of bumps. It's 2 bumps out of the total number of bumps times the length. So if I have 5 bumps, it's going to be 2/5 L. If I have 15 bumps, it's going to be 2/15 L. Again, you can see by this point we're at 4 nodes, 3 antinodes. This would be F3. That is, of course, the third harmonic. Or the second overtone. All right, so let's keep going. If we know that the wavelength can always be found by doing 2L divided by N, where N is the number of bumps, N has to be an integer. Really, we start with 1, so shouldn't even be, it really has to be a natural number. And of course, this is the harmonic number. We know that we should be able to get a formula for frequency. Any particular string is going to have a wave determined by how taut it is, what the tension, how heavy it is. But we know there's a relationship that says V equal F lambda times F. That means our frequency if I put this formula in there, I get N times V over 2L. So for any frequency, that would look like the formula. But think about it. F1, if I put the 1 in, is V over 2L. Fn is simply n times f1. You see how that's f1 v over 2L? That's why f1 is called the fundamental frequency. Every harmonic is simply a multiple of that fundamental frequency. If the fundamental frequency is 50, f1 is 50 hertz. The second harmonic is 100 hertz. The third one's 150. The fourth one's 200. The fifth one's 250. The sixth one's 2. They're all multiples of the fundamental frequency. Okay. Earlier when I said something about the sound, I want you to picture that all of these different waves can be going through that guitar string at the same time. You may get a whole lot of the fundamental frequency, hardly any of the first harmonic or the second harmonic. Maybe you get a good little bit of the third harmonic. Those different quantities is sort of the recipe for that sound. They give that stringed instrument its unique sound qualities. All right, let's do an example. In this example, we've got a situation where we've got a string. There's a pulley. And there's a couple of little tiny supports right here. There's a support. There's a support. It's sitting on a table. And here's a pulley. Hanging off this pulley is some mass. Now this mass hanging off the pulley is what gives that string its tension. But we're interested in the point from here to here. That's going to be the wave portion. That's the vibrating portion of this string. It says if the fundamental frequency is F. So the fundamental frequency F1 there, we're just going to call F. With mass M. What is the fundamental frequency with mass 4M? In other words, how does quadrupling that mass change the fundamental frequency? Well, the first thing that should be obvious is increasing that mass changes the tension, right? Which in effect changes how fast that wave will travel. We know that that a wave speed can be given by tension over mass per unit length. There's our formula, square root of the tension over mu. If F1 then is equal to V over 2L, I can make a new formula. I can say, you know what? The fundamental frequency is 1 over 2L times the square root of that. I'm just putting some formulas together that I know. All right, we know that the tension depends on the mass. If I quadruple the tension by quadrupling the mass, right? If this is 4 times bigger, we know that Ft is equal to mg. So the new one is going to be 4 times as big. All I'm going to do is put that in there. So my original one is this. My new one okay, the only difference between those two is that square root of 4, which is 2. This is going to be exactly like 2 times, and then I would have 1 over 2L square root. You can see what happens if we make this mass 4 times bigger. This new fundamental frequency is simply twice as big as the original fundamental frequency. By quadrupling this mass, I double the fundamental frequency of that string. Let's do one more problem, and we're going to be through with standing waves. This is example 12.3, and it deals with a guitar string. I'm not going to write every word because you can look at it in your book, but they tell us that this guitar string has a length of 0.86 meters. It has a mass per unit length of 0.015 kilograms per meter, and it has a fundamental frequency when you pluck it of 41 hertz. The first thing they ask us to find is the tension. Okay, well, to do that, I'm going to use the fact that I just moments ago combined those formulas that said F1 equal V over 2L, and V is equal to the square root of the tension over mu. So when I put that in, I got this kind of new formula. This may not be your favorite part of physics, but it was actually always one of mine. Now, if I had this valid formula and this valid formula, I could substitute one formula into another formula and create a new valid formula. So I have this. I know that F1 is 41. I know that L is 0.86. And I don't know this. Do I know the mass per unit length? Oh, they gave it to me, 0.015. Now, I can start solving from there, but honestly, I kind of want to erase it. I'd rather solve for f of t without all these numbers. Now, if you prefer numbers, you can do numbers first. Let's just get rid of the 2L. So I have 2LF1 equal this. I just multiplied both sides by 2L. If I square both sides now, I get 4L squared F1 squared equal Ft over mu. So now I get that the tension, when I multiply by the mu, is simply 4L squared F1 squared times mu. Now I'm putting my numbers. Put all of those numbers in. And I get 74.6 newtons. I want to redo this. I actually did it differently when I did it before. Let's see, maybe I didn't do it differently. I thought it looked different. All right, let's get to some double checking. I'm going to turn my phone down. I don't know if you hear all the little dings. 4 times 0.86 squared times 41 squared times 0.015, 74.6 newtons. Thought I did it. All right. So far, so good. We answered part A. We really only had 2 significant digits, so there's our answer. But I'll write that just in case we have to use it in a future part. I don't want to round it if I don't need to. The second part of this question says, find F2 and lambda 2. Well, this one's great because simply F2 is simply double F1. That's going to be 82 hertz. We know that lambda n is 2L over n. So if I want to find lambda 2, it's 2 times 0.86 divided by 2. It's just 0.86 meters. That makes sense because when we're talking about the second harmonic always has a wavelength that's exactly equal to the length of the string. All right. They do ask us to go on and find F3 and lambda 3. If I want to find F3 and lambda 3, that was actually B. So for part C, this is the easiest part of the question. F3 is simply 3 times 41, will be 123 hertz. We can actually keep all of those in our answer because this 3 is not a measurement. It doesn't limit our significant digits in any way. It's more like adding. It's like 41 plus 41 plus 41 because that 3 is exact. So we can keep all 3 digits there. Lambda 3 is 2L divided by 3. So it's going to be 2/3. So 2/3, 2 times 0.86 divided by 3. This we really do only have 2 significant digits. So it's going to be about 0.57 meters. All right, that takes care of standing waves. I'm going to do one more video that really thinks about the process of hearing. What does it mean to hear a sound? How do we measure that sound intensity? What is a decibel? What's loud? What's quiet? So, one more video and we'll have chapter 12 taken care of.